Southwest Oregon has a rich, diverse, and complex geological history. Geological features in the region range from the ancient Klamath Mountains to the geologically young High Cascade Mountains. The flat-top mesas of the Table Rocks, with their own unique geologic history, provide a look into the forces that shaped and continue to shape Southwest Oregon. The Klamath Mountains, which include Mount Ashland, are a rugged tangle of mountains that occupy northwestern California and southwestern Oregon. The northernmost range of the Klamath Mountains, which connects to the Cascade Mountains to the east, is known as the Siskiyou Mountains. The Klamath Mountains were formed at the bottom of the ocean off the ancient Oregon coast. The action of plate tectonics accumulated these distinct rock layers against the stable North American plate at Oregon's margin or plate boundary. One way to look at the Klamath Mountains is as rocks that were formed off the coast. Plate tectonics caused these rocks to rise, causing the state of Oregon to become larger. The rock types of these terrains are over 200 million years old and include volcanic and metasedimentary rocks, ophiolite, schist, sedimentary sand, mudstone, and shale. It is thought these terrains of the Klamath Mountains were joined to the stable North American continent in the early Cretaceous period. Due to the complex topography, geological diversity, and location at the junction of several different ecoregions, the Klamath-Siskiyou region is renowned as one of the most biodiverse places in North America. In the late Cretaceous period, southwestern Oregon was inundated by a shallow seaway which deposited a layer of sandstones and mud rocks, known as the Hornbrook Formation. These sedimentary rocks, which contain marine fossils such as ammonites, gastropods, clams, and shark's teeth, are exposed along the flanks of the Klamath Mountains south and east of the Rogue River.
So, about 60 million years ago, the Klamath Mountains, which are over to our west, the Klamath Mountains are made up of metamorphic and igneous rocks that are very old. So the rocks over there are anywhere from 145 million to 200 million years old. So they're significantly older than, any of the rocks or geology in our area. And about 60 million years ago, there was a period of erosion where the Klamath Mountains were eroded, and you essentially produce what we call an unconformity, which is just an erosional surface that kind of planes off the older rocks. About 40 million years ago, there were rivers and streams flowing through the area that deposited extensive gravels and sandstones. And these units are referred to as the Payne Cliffs Formation. And the Payne Cliffs Formation runs all the way up and down the Bear Creek Valley. If you're over near Phoenix and you look to the west, you'll see these kind of very broad cliffs on the eastern side of the valley. And those broad cliffs that you're looking at are part of the Payne Cliffs Formation, which is made up of these sandstones and conglomerates. About 15 million years ago, the Klamath Mountains were uplifted, and when they were uplifted, they tilted, and they tilted all the sedimentary rocks that were deposited on top of those older rocks. So now these rocks that were deposited by rivers and streams and produced layers of sedimentary rock were then tilted, and they were tilted more or less to the northeast. At this time, after the uplift, there was another period of erosion, so you eroded that surface. So now these rocks were once horizontal or tilted, they've been eroded off.
During the Oligocene period, the area witnessed the birth of volcanoes, forming a range called the Western Cascades. These volcanoes, no longer active, deposited thousands of feet of volcanic mud flows, volcanic ash, and lava flows. Most of the rock formations they deposited have undergone extensive erosion.
And then about 7 million years ago, after this erosion was taking place, you had the beginnings of the High Cascades volcanoes that started to form, and you had lava flows and volcanoes that were beginning to erupt, and you had a very large lava flow that erupted from Olson Mountain. So Olson Mountain is up near Lost Creek Lake, Lost Creek Reservoir. You can't see the volcano anymore. All you see is the eroded remnants of it. but you could see this lava flow that kind of starts up there, and you could trace little pieces and fragments of it all the way down here. So at one time there was this large lava flow, 7 million years old, that flowed down the ancestral Rogue River Valley. So it essentially flowed down and kind of filled in the whole valley as it flowed down. And then since then, erosion has taken place. And what has happened is erosion has cut down along the Rogue River, and has cut down and eroded down into the Payne Cliffs Formation, these sandstones that we were talking about. And the sandstones and conglomerates are more easily eroded. So they tend to be more easily eroded by the Rogue River or the ancestral Rogue River, and then leaving behind only the areas that are the most resistant, that are capped by these lava flows. So the term that we kind of give this type of geological process is called inverted topography. So what was once in the bottom of a valley is now at the top of a hill. And currently the table rocks here are about 800 feet above the level of the Rogue River Valley. So there's quite a bit of erosion that's taken place, and then leaving behind those remnants of table rock sitting up high. There's another diagram that's really great in kind of illustrating the same idea, and this is the one that was put together by the BLM. And again, what it shows is it shows the ancestral Rogue River Valley, and then about 7 million years ago you had the eruption of Olson Mountain, you had lava flows. The lava flow is actually called andesite, which is a type of the volcanic rock that makes up the lava flows. And that lava flow came down and filled in that ancestral Rogue River Valley. And then over time the Rogue River began to cut through and erode the underlying material, and then you had slumping and other processes that essentially started to remove a lot of fragments of the lava flow. And then you had even smaller remnants that were preserved, and then finally you only have a few remnants of the lava flow preserved. Now there's lots of fragments of this lava flow. Upper Table Rock and Lower Table Rock are the most prominent. So if you actually hike Lower Table Rock, get to the top, and actually look to the west, you can actually see another peak that's capped by the same lava flow, and I believe that's called Castle Rock. So Castle Rock is another example of this hill that's capped by a lava flow. And then if you go to Lost Creek Lake or Lost Creek Reservoir, if you drive around, and you don't go into the fish hatchery, but you stay on the highway and go up the hill, if you look to your right, you'll see this you'll see these columns of material along the highway road cut. That's the same lava flow. So you can find portions of that same lava flow up near Lost Creek Lake. So you can find little bits and pieces of it along the ancestral Rogue River Valley.
How can we tell all the lava came from the same eruption?
There's not very many remnants from Upper Table Rock to Lost Creek Lake. But what's been done is the geochemistry, looking at all of the different elements and looking at the specific composition of this material plus its age, and then comparing it to what's up at Olson Mountain. And there's actually a paper that was published in Oregon Geology by Frank Ladke that essentially goes through and talks about the similarities of the lava flow here, the lava flows up there, the age of the lava flow, and makes that connection.
How do we know the lava flowed from Mount Olson to the Rogue Valley?
I have one more image for you, and this is kind of a smaller image, and I'll pass this around. But this is an aerial photograph of Upper Table Rock. So in this aerial photograph, what you can see is there are all these fractures that also occur on the surface or on this lava flow. And if you look at the fracture patterns, if you look at a lava flow, sometimes you can kind of see the flow pattern of the lava flow as it produces, as it flows along. Well, those fractures are pretty diagnostic of, they're always kind of perpendicular to the direction that the lava flow moved. And if you look at that joint pattern as well, that joint pattern is very, very much almost north-south, which would mean this thing's coming from the east and flowing to the west. So that also, suggests that this thing was one large sheet versus something that, if it curved around, you would actually see those joint patterns kind of fall along those curves. On the surface, the way you can find these fractures are the places where you get more soil and the rocks break down, and they're places where water can reside. So often on top you'll see these kind of grassy pathways that kind of go across Table Rock. Those are the joints. So those joints are where water and soil and vegetation kind of accumulate.
By the late Miocene period, the Rogue River had carved through much of the sedimentary rock of the Payne Cliffs Formation and the volcanic rock of the Western Cascades to form a broad valley that was 600 feet higher than it is today. The table rocks are two of the most prominent topographical features in the Rogue River Valley.
What exactly are the table rocks?
So Table Rock is the local name, and if you were just talking about the geomorphic features that you see on the landscape, you would call these buttes. So flat-topped, it has something to do with the layers of the rocks, kind of flat-topped butte, essentially.
Though many people assume Upper Table Rock is taller than Lower, the table rocks are actually named for their relative positions along the Rogue River.
The Lower and Upper Table Rock are the position on the river. So upstream, Upper Table Rock, downstream, Lower Table Rock.
Unlike the surrounding rounded hills in the valley, the table rocks have flat-topped summits that abruptly drop to meet the valley floor below. The elevations of both table rocks are just over 2,000 feet above sea level, and both have a horseshoe shape.
The horseshoe shape is kind of interesting, and if you look at the horseshoe shape of table rocks, the horseshoes are kind of pointing in the same direction. And originally, one idea would be what? What do you think those horseshoe shapes could represent? Yeah, it could be the old river valley, you know, and sometimes rivers meander and they curve around, and if you formed a canyon like that, you would have a lava flow that flows along and kind of fills in that meandering river. So there's a couple of issues with that. Number one, if you look at the modern Rogue River, the Rogue River does meander in some places, it does curve along, but if you look at the size of the river and you look at the shape of these bends, well, if that were the case, then the river would be much, 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 much larger in the past, right? The second thing that's kind of interesting about that, so, you know, you have these horseshoe shapes, they may represent some of the valley, but you have other remnants of the lava flow around. So if it was just confined to the one valley, you wouldn't find as many of these little remnants left over. So that suggests that there was a sheet of lava rather than it flowing kind of in a canyon, okay? So the other option, and this is something I've thought about as explaining the horseshoe shape, is if the Rogue River is down here, that's where most of the cutting is taking place, right? So the river's cutting down, it's cutting down and producing this floodplain. The Rogue River has deposited a lot of gravels along with Bear Creek over the Medford and White City area. It's eventually cutting down. And what often happens with rivers and streams as they cut down is their tributaries also cut down, right? So as the Rogue River is cutting, so is Bear Creek. Well, the same is true for these little tributaries that are migrating to the north, right? And these little tributaries migrating to the north are producing valleys. So you can see that this particular one has been really sculpted and eroded. And most likely, these streams that are kind of migrating to the north have also penetrated some of the Table Rock's lava flow. And that may also be another explanation for why they're horseshoe shaped. Simply these tributaries beginning to cut from the Rogue River as it drops down to the north. Okay, but you know, right now those are just hypotheses. So no one has gone out and really, you know, pinned down exactly the explanation for the horseshoe shape, but there's a couple of explanations for you.
In addition to flowing water, other erosional forces have contributed to breaking down the lava flow. Water freezing and thawing in the cracks of rocks, the root system of plants loosens soil and rocks, the acid released by lichens breaks down the rocks, and wind.
Now you have to remember, you know, this thing's been eroding for 7 million years. And that's another question, you know, when you go to the top and you're walking across the top of the Table Rocks, you see a lot of rock. And a lot of people ask, well, where's all the soil? You know, if this thing's been eroding and soil development's been taking place for so long, then why do we even still see rock on the top surface of Table Rock? And what do you think is a good explanation for saying, you know, where's all the soil? The wind. So, you know, yesterday is kind of interesting. I was telling the students this, we got to the top and then we started seeing dust devils on top, where you see all this dust kind of get going and then blows off the side of Table Rock. So you have a lot of wind that takes a lot of the sediment that breaks down at the top of Table Rocks and blows away. So this thing's been eroding for a long time, and we don't have the top surface of the lava flow anywhere preserved. It's long gone. So that erosion also, you know, plays into elevation changes of that old lava flows that came down.
Erosional processes continue to shape the landscape and break down the table rocks. It is likely someday upper and lower table rocks will no longer be the prominent features in the Rogue Valley they are today.
So this is our first stop, and what we're looking at here is some of the Payne Cliffs sandstone and conglomerate. And I mean, right here we're looking at the sandstone. But this is the older lying material below the Table Rock lava flow. This stuff was the material that was eroded, and then the lava flow came down over top of it. And if you look at it really carefully, you can see little grains in the rock, and when those grains are solidified together, we call them sandstone. So after they made this trail a little bit larger, so when I first came up here, there weren't very many exposures along here, but the trail's been getting a little bit bigger over time. In this little cut, they exposed some of this sandstone, and it's pretty rare to find little exposures of this, but this is one of the little places along the trail where you can actually find and see some of the sandstone. The second thing at this stop is this is our safety lesson of the day. So if you look at the base of this rock, you'll see this really wonderful looking plant with the really shiny leaves that come in threes, and that's poison oak. So there's poison oak all over the hillsides around upper Table Rock, lower Table Rock, and you got to be really careful to stay on the trail. Some of the poison oak encroaches on the trail, so you have to be careful not to brush against it in some cases. So you just want to be careful as you go along the hike today. When the leaves first come out of the plant, they're kind of reddish in color, so some of the reddish colored shiny leaves that you see along the side are also poison oak. So you want to stay clear of that. Try to avoid getting exposed to poison oak today. And then the third thing that we could do at this stop is talk a little bit about these large blocks that are sitting here. These large blocks are called monoliths, and monolith just means one rock, right? Literally means one rock. So these are monoliths. These are large fragments or columns that have come down from Table Rock, or the landscape has been eroded and these blocks have slowly kind of tumbled or rolled, or as the landscape has eroded, they've dropped in elevation to where we see them today. And this thing definitely has been moved because when we look at this surface here, so when we look at the front surface, you could see all these little polygonal shapes. You could see all these little kind of, you know, 5-sided, 6-sided, various sizes from this surface. And then when you look at the side of this particular block, you can see that these polygonal shapes actually form these large columns that go back along and parallel to how the rock is laying down. So these are called columnar joints, and columnar joints form in lava flows. When the rock cools, what happens is, just like you have mud in a mud puddle and the air dries and evaporates the water, the mud shrinks to form cracks. The same thing happens with lava. When it cools, it shrinks and it forms these cracks and actually forms these very long columns. And just like mud cracks, they form vertically. So those columns form vertically through the lava flow. So when we see a block like this, we know that it's no longer in the same position in which it formed. It's tumbled over, it's actually tilted downhill, and either we're looking at the top or the bottom, right? So we're looking at the top or the bottom here of these columns. And then those larger fractures I showed you on the aerial photograph, those larger fractures are essentially cutting through the whole lava flow and are on a larger scale than the columnar joints. but they also help break the rock into larger columns, kind of like the monolith we see here. Anyone notice a change in the character of the trail?
Yeah.
Yeah, I got a lot more rocky around those last few bends, and what's going on is we're getting near the top, and you got a lot of this material coming off of table rocks, weathering away, breaking down, and it's accumulating at the base of those cliffs, base of table rocks. And right over here, there's actually an area that's not so vegetated. And this material over here is talus. We call that talus. That's a talus slope where broken down rock and material kind of accumulates at the base of a cliff or a base of a rock exposure. And then where we've been hiking on the trail, that talus is actually mixed in with soil and other material. So we call it mixed in with soil and other material. We call that colluvium. And then when we get a bare slope where we can see the rocks, we call that a talus slope. But when you get closer to the top of table rocks, that becomes very abundant because that stuff's coming off and weathering off and breaking off from the cliffs at the base of the lava flow. At this point, the talus has essentially filled it up all the way to the top of the flow, or the top of the exposure of table rocks. So the trail actually will take us right to the top, and we won't have to climb over a talus slope, or we won't have to climb over a cliff, essentially. So this is a great place to kind of end our tour. Great view of Mount McLaughlin, Brown Mountain, some of the high Cascades, Western Cascades, Roxanne Peak. You got the Bear Creek Valley going off to the southeast, the Rogue Valley in front of us. See the terraces out there, kind of White City and Medford's Industrial Park areas. Just quite a spectacular view. Klamaths, and you can actually see some of the more distant peaks in the Klamaths that have a little bit higher vegetation, a little bit more snow on those peaks out there. And then this is just a great surface to explore. Not a lot of trees up here. Again, earlier in the spring, there are vernal pools, there's fairy shrimp, all kinds of neat things to explore. The wildflowers also are spectacular up here, so you can go explore, check out a lot of the wildflowers up on top of the Table Rock Butte. But just a pretty spectacular place to come visit, and not that bad of a hike up here either. So just a spectacular place.